Hi everyone, I'm Michael Ram. I'm an assistant professor in the engineering department at UMass Boston and PI of the Ubiquitous Communications and Networking Lab, or UCAN Lab. Today I'll be presenting my team's work on the design and implementation of a heterogeneous multi-hop optical wireless communications and RF relay architecture for opportunistic ultra-dense wireless networks. This work was part of a senior design project by two undergraduate students who worked in my lab, and those students are Jolly Lee and Rex Lee. In this presentation, I'll quickly run through the following points from our paper in order to introduce the proposed architecture. First, we'll provide some background and motivation for the overall design. Then we're going to introduce the architecture and describe how it addresses a few key challenges of network densification. We'll then describe our testbed design that's used for the proof of concept implementation in order to evaluate our architecture. And finally, we'll discuss our experiments and results of the testbed that demonstrate some of the architecture's potential to broadly distribute supplemental optical wireless communications capacity to devices that are either not enabled with optical wireless or are not well suited for network connectivity through optical channels. To begin, we can think of the big picture objective here, our motivation, which ties to increasing area traffic capacity in terms of bits per second per meter squared, or area spectral efficiency, similarly bits per second per hertz per meter squared. You're probably familiar with this image here, the kind of key ways to increase this area traffic capacity and increase network performance in modern networks. And of course, one of the primary ways to increase this capacity in previous decades has been this concept of network densification. In other words, more access points with smaller coverage area densed in to increase your resource reuse. So with this in mind, the first challenge that we want to address is essentially that infrastructure constraints sort of limit the continued network densification with conventional RF wireless LANs or RF access points, right? We have all these devices getting more close together, but we need to actually create a connection to our core network or backhaul network if we want to connect a wireless access point and router in a more dense distribution. So one potential solution to this is the use of directional communications, which allow us to move our access points and the overall infrastructure further away from the working surface while still creating a relatively small coverage area at the working surface, right? And so in this image we have two optical wireless access points, optical wireless communications being one of the many possible directional communications technologies, and the one that we specifically focus on in this work. And what you can see here is that these two optical access points have smaller coverage area within the broader coverage of this RF wireless LAN or RF small cell, and we get that improved resource reuse and overall increased area spectral efficiency or area traffic capacity. The second challenge in this kind of environment, though, is that many of today's wireless devices have a very broad range of mobility characteristics. So for example, in this scenario here, we've connected these portable devices or laptops, which are typically used in a relatively static position, and use those to connect to the optical wireless channel. However, some of these mobile devices, for example your smartphones, tablets, and things like this, are poorly suited for use of the optical wireless communications. So we can offload some of this traffic with this optical wireless communications access points, but much of the traffic and congestion still goes towards our wireless LAN. Now the potential solution and the novelty of this proposed work, or the work that we present in this paper, is this idea of opportunistic heterogeneous optical wireless and RF relays. So in other words, we can utilize the optical wireless communications for these portable or quasi-static devices, things like your laptop, like I mentioned before, but then we opportunistically use these devices that are connected through optical wireless as relays to provide a local RF connection for mobile devices. So now we create a low power, small scale, ultra dense RF wireless LAN or personal area network, or something that's a much smaller coverage area here. And in this case we can connect some of these nearby mobile devices and use that portable device as a relay to route traffic back to the network through the optical wireless access point. And so the outcome here and the goal of what we're trying to do is then distribute that optical wireless capacity, which It can be relatively drastic in the environment, but we're distributing that across devices that wouldn't otherwise be able to utilize the optical wireless capacity, and removing some of this congestion from our primary RF network. Some of the benefits are that we have some opportunistic use of these portable devices. We're distributing that traffic and that capacity to improve the utilization of the RF resources. And as a secondary sort of benefit, we can consider power consumption trade-offs for portable and mobile devices, as these mobile devices can actually reduce their power to connect to the nearby relay access point at the cost or expense of increasing the power consumption of that portable device, which is typically less power constrained. In order to make this a more practical architecture, we start with the conventional 802.11 architecture design, where we have various stations connected within a basic service set. In order to extend this, we use our distribution system to connect multiple basic service sets through access points, or to connect to the distribution system through access points, and then we create this extended service set to increase the overall coverage range of our wireless network. Our proposed architecture extends this by essentially adding the optical wireless channel as part of our distribution system, and then opportunistically using some of these mobile devices to create these relay basic service sets in a more dynamic pattern. Right? So our time scale is a little bit different here. Rather than setting up our network at one specific time, we can consider these relay basic service sets either coming in and out of the network and dynamically changing the extended service set at a more frequent time scale. Right, so our goals here, we extend this distribution system, and then we have these dynamic basic service sets that would conventionally fall under that coverage of our primary basic service set. So now in order to evaluate this architecture, we've developed a test bed. This is a good portion of the paper describing what we've done in this test bed, but the big picture idea of what I'll discuss today is that we have a centralized test bed controller connected to a number of nodes created as Raspberry Pis that are able to be configured as various access points or user devices in a variety of different ways. Right? And we basically, in our analysis within this paper, set out to observe these three specific experiments in order to evaluate some potential performance of this architecture. In our first case, experiment 0 here, we have our ground truth scenario where we have 4 stations, all of which are connected back to our primary access point with Wi-Fi. In our second experiment, basically experiment 1, we've taken the first step here where we implement optical wireless communications offloading. In this case, we use an emulated optical wireless channel, and we offload station 4 to this optical wireless link, essentially removing its traffic from the Wi-Fi network. Lastly, in experiment 2, the focus of this paper, really demonstrating this novel architecture, is the implementation of station 4 as an opportunistic relay and connecting station 3 through that 4th station or the introduced relay here. The results, we'll talk a little bit about the downlink and uplink results. In experiment 0, our base case, as you can imagine, the performance of each device reduces as the distance increases. In this case, we throttle our Wi-Fi and our optical communications performance just to kind of have a more comparative result here. The basic outcome from this initial ground truth experiment is, as I mentioned, the throughput reduces with our distance. So that station that's furthest away, kind of at the edge of our Wi-Fi cell, has the least or the lowest performance. In experiment 1, as we've offloaded this to our emulated optical wireless link, we now see that we've increased the capacity of station 4, or the throughput of station 4, basically because it now has full access to that optical wireless link. Right? Secondary impact of this is that there's now reduced contention on the Wi-Fi network, so our RF throughput increases for stations 1, 2, and 3. The total throughput there goes up, and our aggregate capacity in the environment increases. This is kind of the well-known and well-explored outcome for supplementing your wireless LAN with this optical wireless communication, and we've seen this in prior work. The novelty of this proposed architecture comes in experiment 2, where now we've offloaded station 3 from the primary access point in order to route its traffic through this opportunistic relay or station 4. In this case, The throughput of Station 4 is reduced a bit here because it's now sharing that optical capacity, as Station 3's traffic also has to route through that optical wireless link. But Station 3 has an increase in its throughput because it's now receiving a better connection on the RF channel to Station 4 and able to route its traffic that way. Also, our total throughput from the primary access point increases because we are able to do some power separation or distinction between the transmission from Station 1 and Station 2 and that transmission from Station 3. Even though there's some contention there, it's less than in our previous case. Essentially what we've shown here is that our aggregate throughput is comparable for both experiment 1 and 2, right? So the supplemental optical wireless capacity essentially increases the capacity in the space, as you can imagine, but the unique contribution here is now our fairness improves. We're better able to actually distribute that traffic across different devices. And we see similar trends in our uplink. Right? The bottom three plots here are just showing the similar relationship for uplink performance in experiment 0, 1, and 2. Our uplink for this experiment 2 is actually a little bit higher than in the downlink scenario, assumedly due to the primary access point being further away or having less contention on that uplink with the relay on the other side of things. We can also observe the total RF throughput in comparison between experiment 1 and 2, and we see that we're getting better utilization of the RF channel in experiment 2. In this case, both the relay and the primary access point are using the same RF channel, so still competing for resources, just using some power allocation in that case. However, there's also the option to set the relays or various relays as different orthogonal channels. So in conclusion, we have a couple of key observed outcomes. Our supplemental RF network, or we've supplemented the RF network with the optical wireless capacity, allowing portable devices to be offloaded to the optical wireless links. This increases our overall network capacity, and this is a result that's kind of known from literature previously. The primary novelty here is that we opportunistically use these devices that are on the optical wireless channel as low power RF relays, and they are now able to connect nearby mobile devices, which gives us this opportunity to distribute our optical wireless capacity and improve the overall fairness in the network. Lastly, as a secondary effect, something that's going to be observed in future work is this idea of a reduced power requirement or trade-off here for devices that are connected to the local relay devices. And as I mentioned earlier, this is giving us a trade-off between an increased relay power consumption of that station that's a portable device for reduced power consumption from our mobile device, like the example in Station 3 here. Other future considerations, the scalability of this, how things work and how this performance scales with additional optical wireless access points and relays in a particular environment, how that channel selection impacts performance. For example, as I mentioned, using orthogonal channels between your basic service set and the relay basic service sets, how that power allocation can actually dynamically adapt to remove some of or to change the size of those relay basic service sets. Also just to kind of consider a key question here is the motivation for a relay to behave in this way, a relay station. Other possible options that we incorporated here discussed in the paper relate to energy harvesting, potential policy incentives, some power limitations that minimize the use of that power as a relay, and so on. So that concludes the overall discussion for this paper. Thank you very much. Open for questions.